Alright, so in this video we're going to solve the equations for the Ekman balance and derive the solution to these equations that will show us the Ekman spiral that you get at the surface of the ocean. Alright, so we have two equations. The first one represents the X momentum balance. Remember, this is the Coriolis force per unit volume, and this is the convergence of the momentum flux due to eddies, the vertical component of that, the vertical convergence. And this one is the Y momentum equation. I have again the Coriolis force, and then in the Y direction per unit volume, and then against the convergence of northward momentum in the vertical. All right, so we have two equations, equation 1 and equation 2. So these equations, if you notice, if you look at them, there's only one independent variable. So the first point is there's one independent variable, and that is namely z. So the z is the independent variable, and then ue and ve are the dependent variables. So two dependent variables, namely u sub e and v sub e. So these are the functions. These are functions of z. And that's the goal, is to try to find these solutions. What is the functional form of u as a function of z, which is the depth? These equations are differential equations, right? We have derivatives. I wrote them as partial derivatives because they showed up in the momentum equation where there was derivatives with respect to time and with respect to the horizontal coordinates. But in this expression, since there's only one independent variables, these partial derivatives can in fact be expressed as ordinary derivatives because we only have derivatives with respect to z. So these are in fact two ordinary differential equations. And what else can we say about these? They're second order, right? The highest derivative that shows up are the second derivative, so they're second order differential equations. Another thing is that they're coupled, right? You notice that both VE and UE appear in the first equation, and UE and VE appear in the second equation. So you can't just integrate one equation and get the solution for VE. Like you would think maybe you can integrate this one twice, and then you'll get an expression for VE, but we don't know UE. So if we come to this equation, the same problem is that UE and VE appear in both. So they're coupled equations. What else can we say? Well, one thing that is good about these equations is that they are linear, right? So VE doesn't appear like a quadratic or inside a sine or cosine. They're all just linear expressions. The derivative is a linear operator on UE and over here also. So they're linear. So they're linear equations. And one more thing is that all these coefficients out front, we're going to take them to be constant. So in reality, f is a function of latitude, the Coriolis parameter. Density is a function of space. The viscosities, the eddy kinematic viscosities can also vary with depth, but we're going to take them to be constants here. So they're going to be constant coefficients. So we're going to take all the coefficients to be constants. Only u and v will be functions of depth. And now we're going to try to solve these equations, and we need to solve this, since these are differential equations with second derivatives, and there's two variables, we're going to need 4 boundary conditions to solve these equations. So in general, when you integrate, each time you integrate, you get one integration constant. So if we have 4 derivatives, 2 on UE and 2 on VE, then for each integral we're going to get an extra integration constant, so we'll get 4 integration constants, and therefore we need 4 boundary conditions. And the boundary conditions we're going to use are, we're going to apply this to the surface of the ocean, And so we're going to think of the domain is the z direction, z, and this would be the C surface at z equals 0. And what we're going to think of is at the surface, we're going to apply a wind stress. So we're going to apply the wind stress at the surface, and we're going to match the eddy stress in the ocean to the wind stress at the surface. So those are going to have to match at the surface, and that will be our boundary condition. So at the top, we're going to impose the wind stress, tau, and to make things simple, we're going to assume that the wind stress is only, the vector is tau x. Let me erase the title here. This tau will be tau x and 0. So the horizontal stress at the surface will be totally in the x direction, just to make the problem simpler. So we'll assume there's no northward component of the wind stress in this problem. And so the boundary condition is going to be so tau x, so at the surface, this is the wind stress, tau x. So that's the flux of momentum. I'll put a little wind here to remind you that's the wind. Wind. So that the condition is that the flux of momentum per unit area, that's the stress, into the ocean from the wind has to be equal to the flux, the eddy flux of momentum in the ocean. So the eddy stress in the ocean is minus rho naught AV UE dz, right? The first derivative, this is the flux of eddy stress. Now this is the, with the minus sign, this is the upward flux, and whereas the wind is the downward flux. So if we want these to match, we need the plus sign over here, right? Because this one is a flux into the ocean, and this one with the plus, which is the negative of the usual flux, we usually have the stresses be positive upwards, that would be downward. So now these have to match. So that's the matching condition at z equals 0. So we have this condition, and then for the y component of the wind, well, that one is just equal to 0. So if I rewrite it, we have 0 is equal to rho naught AV dVE dz. So in the northward direction, there is no wind stress. We've prescribed it to be 0, and so that is equal to the eddy stress in the ocean. The negative of the eddy stress is 0, but it doesn't matter if you have a negative since it's 0 in this case. All right, so that's 2 boundary conditions. We need 2 more, and I guess in general we would apply the 2 other boundary conditions at the bottom of the domain. So, right, so this is like a boundary value problem. We have a boundary condition over here, and we're going to have another boundary condition deeper down somewhere. And we're going to see when we go to solve it, we're going to use the fact that at the very least, the solution UE and VE should not blow up as we go into the deep ocean. So the wind is applied at the surface, and the velocity shouldn't be getting bigger and bigger and bigger as we go deeper down. So we're going to use the condition that UE and VE are bounded as z goes to minus infinity. So is that z minus infinity is able to go deeper down into the ocean. All right, so these are our 4 boundary conditions. We have 1, 2, and the one that UE will go to remain bound, doesn't blow up, and same thing for VE. All right, so I pointed out already that we have 2 equations and they're coupled. One way to solve it is to solve it numerically, and we're going to do this as an introduction to finite difference methods. But the first thing we're going to do, we're going to solve it analytically. So solving it analytically, getting explicit expressions for the solutions is tedious, but it's not too hard. So I wanted to show you guys how you do this so that you'll understand where the solutions come from if you see them in a textbook or on Wikipedia or something. So we're going to solve the equations, and we're going to get the answer. We can solve it in this case analytically because, again, they're linear constant coefficient differential equations. They're coupled, and so we're going to uncouple them. And the way we're going to uncouple them is by taking 2 derivatives with respect to z in this equation on both sides, and then here we'll have the second derivative with respect to VE, and we also have the second derivative with respect to VE over here, and we're going to replace it by UE. And then we'll be able to eliminate all the V's in the top equations. So let's do that. So remember the boundary conditions, we're going to use them later. But for now, we're going to uncouple the equations. So uncouple the equations. So we're going to do d2 dz squared of 1. And if we do that, we're going to get minus rho naught f d2 ve dz squared is equal to rho naught av d2 ue. No, not d2. Now we have a fourth derivative, right? We used to have a second. And if I differentiate 2 more times, I get a fourth derivative, dz to the fourth. And then we're going to use equation 2. So solve for dve dz squared from equation 2. And if we do that, we find d2 ve dz squared is equal to, the rho naughts cancel, and so I get f over av ue. So it's equal to f over a sub v ue. And then we substitute in 1, so putting these two together, will give us minus f squared over av, the rho naughts cancel. Oops, the rho naughts cancel. F squared over av ue is equal to av. So I have av over here. I can bring it on the bottom, squared d4 ue dz to the fourth, and I should have a minus sign with a minus over here. So now this equation is the one we're going to solve. This one is a fourth order ordinary differential equation, and it's constant coefficient. All right, so this is the equation we're going to solve. All right, let me make some space. You guys can stare at that equation while I erase the rest of the board. First, let's look at this quantity here, f squared over av squared. So av over f. What are the dimensions of this? So if I look at the dimensions of this, av is the kinematic viscosity, or the diffusivity for momentum, and it has units of meters squared per second. So this quantity will have a meter squared per second, and f is per second. So that's meters squared per second on top and 1 over second on the bottom, which is the same thing as meters squared. Yeah, just meters squared, right? Yes, the per seconds cancel from the top and the bottom. And so we just get a meter squared. So that means that the quantity, I'm going to introduce this quantity delta, which is equal to the square root of av over f. This is a length. This is a length parameter. And what I'm going to do is I'm going to rescale my z variable with respect to delta. In other words, I'm going to measure distance in units of delta. So if my new variable is z equals 1, that means we're at a depth, or z equals minus 1, we're at a depth of minus delta. If z is minus 2, we're at minus 2 delta, minus 3, minus 3 delta, and so on. So just to show you how this works, I'm going to define z star is just z divided by delta. So z at units of length, delta has units of length, so z star is a dimensionless depth variable or height variable. And now I'm going to, if I want to use the z star variable in the equation, I have to figure out how to convert these derivatives with respect to z into derivatives with respect to z star. So we can do this in the following way. If I do dz star dz, well, I can differentiate with respect to z, and I get 1 over delta. I'm using the chain rule. I have d by dz is dz star by dz times d by dz star. And then I substitute this in here, and what I get is 1 over delta d by dz star. So wherever I used to have a z derivative, I now have a z star derivative, but I have to multiply by a factor of 1 over delta. So my equation becomes minus f squared over av squared. This quantity is just 1 over delta squared, right? No, this is 1 over delta to the 4th power, sorry. Right, this is the square root. So if I multiply this with itself 4 times, then I get minus f squared over ab squared. So this is delta 1 over delta to the 4th power on this side times ue is equal to, and then if I have 4 derivatives, I pull out 4 factors of 1 over delta. 1 over delta to the 4th, d to the 4th, ue times dz star to the 4th. And the nice thing now is that these ue's, not these ue's, sorry, these 1 over delta to the 4th powers, they cancel. And so my equation, if I express derivatives with just primes, my equation now becomes simply ue 1, 2, 3, 4 for 4th derivatives is just equal to minus ue. And I'm going to try to solve this equation. Equation is ue of z star 1, 2, 3, 4. 4th derivative is just minus ue. All right, so let's look for a solution of the form ue is equal to e to the lambda, some constant c, z star. And it's getting annoying to have that little star everywhere. So from now on, I'm going to drop the star. So I'm going to drop, I will drop the star from now on, comma, but remember that z is non-dimensional. And at the end of the calculation, I'm going to have to go back and replace, I will have to replace z with z over delta. All right, so the z from now on is a non-dimensional z. At the end, I will redimensionalizing it by replacing z by z over delta. All right, so this is my differential equation for ue in terms of the non-dimensional z. And I also would like to have an expression for what VE is. And if you remember what the equation was, it was minus f, the dimensional one, minus FVE is equal to AV d2 UE dz squared. If I replace it with the non-dimensional equation, the non-dimensional z, then this becomes UE double primed, and this goes away, and this becomes just minus BE, or like this. And so this expression, I can solve this equation because it's uncoupled for UE, and then once I have UE, I can take 2 derivatives, multiply by minus 1, and I'll get the solution for VE. Yeah, so let's solve for these equations. I guess one thing I should maybe do right now, while I'm at it, is specify what the boundary conditions are at the surface in these non-dimensional variables. So the surface boundary condition was that tau, what were the boundary conditions again? At the surface, I had rho naught AV d over delta UE primed is tau x, and rho naught AV over delta VE primed equals 0. So these are the boundary conditions. This is at z equals 0 and at z equals 0. Does the delta go on the bottom or on the top? Yeah. Yeah, on the bottom, yes, when I convert. That's right. Okay, so I'm going to solve this equation. Once I solve for that, I'm going to solve for, take two derivatives and solve for VE. And then I'll have UE and VE. And then I will take one derivative of each and solve, apply these boundary conditions. And we also have the other two boundary conditions that as z goes to minus infinity, the solution remains bounded. And by this I mean it doesn't blow up, bounded. So it can't grow exponentially as we move away. All right, so this constant coefficient linear differential equation, we're going to look for a solution of the form. Maybe I should write these somewhere else so I can keep them. Okay, UE 1, 2, 3, 4 equals minus UE. VE is equal to minus UE double prime. UE primed at 0 is equal to tau x times delta over rho naught AV, and then VE primed of 0 is equal to 0, and then UE and VE are bounded as z goes to minus infinity. Okay, so I can keep these over here because we'll need them later. All right, so we're going to look for a solution of the form UE of z is equal to some constant c times e to the lambda z. And this exponential form is a general form of a solution to equations that are linear and constant coefficient. So UE appears only linearly in these expressions. Derivatives, those are a linear operation, and they have constant coefficients. So it's going to have a solution of this form. So we substitute this in the equation. If I do UE primed, I get c lambda e to the lambda z. If I do UE double prime, I get c lambda squared e to the lambda z. UE triple primed, I get c lambda cubed e to the lambda z. And UE quadruple primed, c lambda to the fourth e to the lambda z. And then I substitute that in there, and I get c lambda to the fourth e to the lambda z is equal to minus c e to the lambda z. And the c's cancel, the e to the lambda z cancel, and what I'm left with is what is called a characteristic equation. Lambda to the fourth power is equal to minus 1. And so I have to find the four roots of this polynomial expression. Maybe I can write it like this. Plus 1 equals 0. So you can see right away that it's going to involve imaginary numbers because if they were real, then lambda to the fourth power would be positive, plus 1, there's no way that would be 0. So we're going to have imaginary parts. And the way to solve these polynomial equations like this with a fourth power or some nth power plus a constant is we go to the complex plane and I write it like this. This is the imaginary part of lambda, and over here this is the real part of lambda. And I want to have lambda equal to minus 1, so I'll put minus 1 over here. And what I do is I divide the arc, so I think in polar coordinates. So if I go from here, this is pi by 2, and then all the way over here, this is pi, right? This is theta equals pi. So if I just go only up to here, then this is theta is equal to pi by 4 over here. This is another pi by 4, a third pi by 4, and this is 4 pi by 4. And so if I look for a solution of this form, e to the I times theta, then if I raise this to the fourth power, what I get is e to the I 4 theta. So all I have to do is divide the pi by 4. So my solutions are going to be lambda is equal to e to the I pi by 4, or I could go, if I can also go the other way around from down here. 1, 2, 3, 4, and I also end up at minus 1. So another root is e to the minus I pi by 4. And then another possibility is to start over here. If this is e to the 3i pi by 4, and so if I square it, I'll get 1, 2, 3, I end up here. If I cube it, 1, 2, 3, I end up here, and if I raise it to the 4th power, 1, 2, 3, I end up back here. So the other two roots are e to the I times 3 pi by 4, and e to the minus I 3 pi by 4. So these are the four roots of this polynomial. Now, I can sketch them. There's one here, one here, one here, and the other one over here. They're all at these 45-degree angles. And what we have to notice now, well, I guess let me write down the solution now that I know what they are. So the solution is going to be ue of z is a e to the lambda 1z plus b e to the lambda 2z plus c e to the lambda 3z plus d e to the lambda 4z, where this is lambda 1, lambda 2, lambda 3, and lambda 4. And if I look at what the forms of the lambdas are, both lambda 2 and lambda 3 have a negative real part, right? The real part falls over here, right? And this is negative, and this is the imaginary part, but the real part is negative for both these roots. And so that means that if I have for lambda 2 and 3, I have a negative real part. When I multiply by z, which is negative, I'll get a positive, so I'll get e to a positive number. And as z gets more and more negative, as I go to minus infinity, this solution and this solution, they will grow exponentially. So these two roots are not good. So these ones here, they blow up. They have a negative real part and blow up as z goes to minus infinity. And so these two constants, b and c, have to be set to 0 to satisfy this boundary condition. So I can apply this boundary condition, and I get that b is equal to c is equal to 0. And I'm only left with the last two boundary conditions, the last two, lambda 1 and lambda 4, because both of these have positive real parts. So as z goes to minus infinity, those solutions will decay exponentially, so I can keep those. So my solution becomes, this is because of this here. So the solution becomes ue of z is equal to a e to the lambda 1z plus d e to the lambda 4z. And then I can rewrite them in terms of exponentials. Let me rewrite them more nicely. Exponential lambda 1 is e to the I pi by 4 z plus d exponential e to the minus I pi by 4 times z. So the z there is down here. It's not in the exponent of this one. It's the exponent of this one, of this exponential. Okay, so now I have to apply my remaining two surface boundary conditions, the conditions on the stress, to find what a and d are. So let's find out what VE is first, VE, and so then I could apply this boundary condition also. So VE of Z is equal to minus second derivative of UE, so I take second derivative of this one. So this will become minus UE double prime would be e to the I pi by 4, and I square it, right? I take these derivatives twice. So, well, I guess I'll just multiply twice for now, times a exponential e to the I pi by 4 z. And then from this one, two derivatives minus e to the I pi by 4 times e to the I pi by 4 d exponential e to the minus I pi by 4, oh, these are minuses, minus pi by 4 z. And e to the I pi by 4 times e to the I pi by 4, that's e to the pi by 2, and e to the pi by 2, right, pi by 4, pi by 2 is up here. So e to the I pi by 2 is equal to I. So this factor here is I, and same thing, this e to the minus I pi by 4, e to the minus I pi by 4 is e to the minus I pi by 2. That's down here. So this is equal to minus I. So over here, I'm going to replace this by I. And down here by minus I. Minus minus makes it plus. So this becomes plus I. Alright, so this is what VE is, and this is what UE is. And then I evaluate these things at, oh no, I take the first derivative of each, and I set z equal to 0. And then I set those equal to that quantity. So if I take the first derivative of UE primed at z equals 0 is going to be A. And if I take one derivative, I multiply by a factor of the e to the I pi by 4. And then I evaluate, I get the exponential, evaluate at 0 is just 1, plus d e to the minus I pi by 4. Right? When I take one derivative, I pull out this factor out front, times d. And then I have, that has got to be equal to tau x delta over rho naught a sub v. And then VE primed at z equals 0. I take out one derivative, so that's equal to minus I e to the I pi by 4 times A. And then evaluate at 0, the exponential goes away. Plus I e to the minus I pi by 4 times D equal to 0. Alright, so these are two equations. There's an equation up here in two unknowns. My unknowns are A and D. And two equations, two unknowns, so I'm going to have to solve these. And the way I'm going to solve these two equations, two unknowns, is using Cramer's rule. So two equations, two unknowns, solve using Cramer's rule, which you may or may not have learned before. Now you'll learn it right now. So I first write it out in matrix form. So I have a matrix times A and D is equal to the right hand side, which is tau x delta over rho naught AB, 0. And then the coefficients are e to the I pi by 4, e to the minus I pi by 4, minus I e to the plus I pi by 4, and plus I e to the minus I pi by 4. I guess I could multiply through, I could divide the I out on this equation, and that will make things nicer, right? Because it's by z, it's is equal to 0, so I'll get rid of these i's and make the algebra simpler. So I divide through by the I, and I wrote the second equation. So the first row corresponds to the first equation. Remember, matrix multiplication is this times this plus this times that is equal to this, and this times this plus this times that equals to that. All right, so Cramer's rule just says that the solution for A is equal to the determinant, so A is equal to the determinant of, and what I do if I want to solve the first one, I replace the first column by the right hand side and compute the determinant. So that becomes tau x delta over rho naught AB, 0, e to the minus I pi by 4, e to the minus I pi by 4, divided by the determinant of the original matrix. So the determinant is this times this, which is 1, minus this times this, which is, in this case, is another one, right? This is e to the plus I, e to the minus I. Multiplied together, I get 1. So it's 1 minus minus 1 becomes 2. So it's easy in this case. And then B is of the same form. It's going to be the determinant And this time, since I'm solving for the, sorry, not B, D. If I'm solving for the second component, I replace the second column by the right-hand side. So I get e to the I pi by 4 minus e to the I pi by 4 tau x delta over rho naught AV 0 all over the determinant of this thing, which again is 2. Alright, so I have the solutions. All I have to do is evaluate these determinants, plug them back into my solution, and I'll have solved the problem. Whew, let's try it out. Okay, let me erase this up here so I have space to write the solution. So the solution is ue of z is equal to a. Where's a? A is here. So a is this times this, so it is equal to tau x delta over rho naught AV, open parenthesis, times this e to the minus I pi by 4 times the original solution, which was exponential e to the I pi by 4 z plus d plus d, and d is this times this minus this times that, so it's again, I get again this factor tau x rho naught over AV, and now I also get an e to the plus I pi by 4, e to the plus I pi by 4 times exponential of e to the minus I pi by 4 z. So that's what ue of z is. And then for ve of z is equal to tau x over delta. Oh, I forgot the factor of 2. Right? I can't forget the factor of 2. So this whole thing has a factor of 2 out here. 2 rho naught AV. And then I have, what was the solution again? I've already erased it. Let me get my notes, and so I can just write it out since I've already erased. You can go back and look at the video. Delta tau x rho naught AV e to the minus I pi by 4 times exponential of e to the I pi by 4 times z minus exponential, no, minus e to the plus I pi by 4 exponential of e to the minus I pi by 4 times z. Like that. Alright, and then we can clean that up a little bit. So let me clean it up a little bit. So one thing we can do is, this is an exponential times an exponential, so we can add the exponents. So I can bring in the minus I pi by 4 inside the exponent I pi by 4 over here and erase that. And similar over here, I can bring in the minus I pi by 4. Oh, sorry, in this one I could bring this inside, and so it's not on the outside. So I get plus I pi by 4, and then this one is gone out front. Plus, same thing here. I can bring this minus I pi by 4 over here, and this one inside. Plus I pi by 4. Alright, and this was a minus, I think. Plus. I think I forgot. This is not quite. Let me check here. Is this right? This is not quite right. There was a factor of I out here, right? Remember when I had e to the I pi by 2? I think I'm missing a factor of I here and here. Is that where they go? Plus plus. I guess it should be minus I and plus I. I think that's right. Alright, so now we're almost ready to clean up the final bit. We're going to use this fact over here. If I know that e to the I theta is equal to cos theta plus I sine theta, remember from the complex plane, if I have a point out here on the unit circle, and this is theta, then this distance here, the real part, is cosine of theta, and the imaginary part is sine theta. So this number here, z, is equal to cos theta plus I sine theta. Right, this is the imaginary axis out here. I mean, I should use lambda like before, lambda. And this is the real part of lambda. So, therefore, if I plug in e to the minus I theta, then I get cosine of minus theta plus I sine of minus theta. And then the cosine function is an even function, right? Cos of minus theta is cos of theta. So I can get rid of this one. This, but sine is an odd function, so this becomes negative, and I just have theta. And then what I can do is add these two equations together. The imaginary parts will cancel and divide by 2. So if I do e to the I theta plus e to the minus I theta and divide by 2, I get cos theta plus cos theta is 2 cos theta, divided by 2 is just cos theta. So I can express this sum of exponentials divided by 2 as a cos theta, and that's exactly what I have over here. I have 2 exponentials, except that the arguments, this one is plus minus, this one is minus plus, so they're just the negatives of each other. So this is going to be a cosine, this part over here. And this part over here has a is going to be like a sine. So let's do this one. Let's create the sine. So if I want to get the sine, I would do this minus this one, and the cosines will go away, and I'll have the sine. So if I subtract one from the other, I get e to the I theta minus e to the minus I theta is equal to this minus or plus 2I sine theta. And so if I want to get sine theta, I just divide by 2I. And so I'm going to bring this 2 in here and this 2 in here, multiply through by I, and get it in this form. Alright, so let's do that. Let's use those facts. So the first expression, UE of z is equal to tau x delta over 2 rho naught AV. Remember, e to the I pi by 4, is equal to, there's a real part and there's an imaginary part to that. That's equal to, right, pi by 4. If this is 1, this is root 2. And so what was I trying to say? Oh, yeah. So, so the cosine, so this quantity is going to be equal to root 2 over 2 plus I root 2 over 2. Yes, and then e to the minus I pi by 4 is equal to root 2 over 2 minus I 2 over 2. And so those expressions over here will become exponential of root 2 over 2 times z, that's for the real part of this thing, and then the exponential of the imaginary part I'm left over, which is e to the, well, is the remaining part, which I said is a exponential plus exponential divided by 2, so if I get rid of the 2 and I bring it on this side, this becomes a cosine. Cosine of root 2 over 2z, and then I have plus or minus pi by 4. And then for the other one, dE of z. So I'm going to multiply through by I on both sides, top and bottom I mean, numerator, so I get an I here. I times I is minus 1, so this becomes a plus. I times I is minus 1, so this becomes a minus. And then I can bring the 2i underneath to get that sine expression, that it divided by 2i, right? I have a 2i in the denominator. So this becomes tau x delta over rho naught AV exponential of root 2 over 2z times sine of root 2 over 2z minus pi by 4. Let me check if I got that right. Yeah, that's right. So I'm gonna, the cosine is an even function, so I can put multiply the argument on the inside by minus 1 without changing it, so I'll put it, so just I follow my notes. Becomes a plus, and then the sine is an odd function, so if I multiply through by a minus out here, then I get a minus out front because it's an odd function. And that is in fact the form of the solution I want. One last thing we have to do is remember that our z here is still the non-dimensional one, so we want to go back to the dimensional z, and so for that we need to replace this non-dimensional z by the dimensional z, which is z over delta. So here, now this becomes dimensional, and I divide, wherever I see a z, I just divide it by delta, divide by delta, divide by delta, divide by delta. And now this is the form of the solution. So there's two parts to the solution. There's this exponential part, right, which will decay as z goes to minus infinity. So this tells us this root 2 over 2 divided by delta, or delta, 2 delta over root 2 is kind of the length scale at which the current decays as we go down into the ocean. And it appears in both the u and v. And at the same time, we have this a circular function, these cosines and sines, and they tell us that as we go deeper down in the ocean, as z decreases, these cosines are changing and the current is going to swirl. So these two give us the spiral of the solution as a function of depth. So the thickness of the Ekman layer, I guess, the thickness, the E folding decay of the Ekman current is delta over times 2 divided by root 2. And so if I multiply top and bottom by root 2, this becomes 2. And so delta times root 2, I guess. This is the length scale, this is the thickness, this here. This is the thickness of the Ekman layer, you could think of it that way. So by the time you go down the depth of delta root 2, you've decreased the speed of the surface current by a factor of e, 1 exponential 1e. And if you go twice this depth, then you have 2 factors of e. And then you notice one more thing is that the wind stress is purely in the positive u direction, right? But there's going to be a v component because of the pi by 4. So at z0, at z equal to 0, this is 0, so we have cos of pi by 4 and sine of pi by 4. And so the current is going to be veered. So if we have a wind stress, there's going to be a 45-degree pi by 4, which is 45 degrees to the right. And so even though the wind is blowing that way, the current is flowing at an angle, 45 degrees. And as we go down into the water column, it's going to spiral and get weaker and weaker. Now there's nothing too magical about this pi by 4. It turns out that this solution depends critically on having picked AV to be a constant, which in the real ocean it's unlikely to be a constant because there's turbulent mixing, and therefore the strength of the turbulence may very well be a function of depth, and AV may depend with depth. And so this pi by 4 angle is not really sacred or anything like that. It's in this idealized model where the turbulent diffusivity for momentum or the kinematic viscosity is a constant as a function of depth. Okay, so I'm going to stop now, and then in the next video we'll solve the same problem again, but this time we'll solve it numerically, which I think it's, well, I guess if you know how to program it seems easier. Anyways, numerical methods are much more general than these analytical methods. So we'll solve it numerically, and we'll go to the computer, numerically at the computer, and we're going to compare both solutions, make sure that everything works out. All right, see you in the next video.